So today we're going to kind of finish our exploration of projectiles, and we are going to launch a projectile vertically. So we've talked about what happens when we drop a projectile and it goes vertically. We've talked about a horizontal throw. We've talked about throwing the ball up at an angle, and now we're going to talk about throwing the ball or the projectile straight up, basically at a 90-degree angle with the horizontal, so perfectly vertical. And we can still use our equations to help us out. So we still have this idea that velocity in the x is v cosine theta and velocity in the y is sine theta. Just realize that when we're talking about a vertical launch, we're talking about an angle of 90 degrees. So let's take a look at example 1. If we want to calculate the initial velocity in both the x and y directions for a projectile launched at 30 meters per second straight up, that means theta is 90 degrees. So my velocity in the x direction is going to be v cosine theta, and my velocity in the y direction is going to be v times the sine of theta. But when you plug in on the x side, when you plug in 90 degrees for the cosine of theta, so if we took 30 meters per second times the cosine of 90 degrees, we would see that that is actually going to be 0. And when we plug in for vy and we say, well, 30 meters per second times the sine of 90 degrees, the sine of 90 degrees is 1, so we're just going to get 30 meters per second. So we can see what we would have expected is that all of the velocity when we throw the ball straight up into the air, all the velocity is in the y direction. None of it is in the x direction. So we can use this because this is going to simplify the problem a lot. So let's go ahead and take a look and see what we've got for one of our examples. So we've got that a rubber ball bounces straight up off a table with a velocity of 18 meters per second. We want to calculate the time it takes the ball to reach its maximum height. So we're going to go ahead and cross that out there. We're going to calculate the time it takes the ball to reach its maximum height. So in the past, over the last few days, we've been listing our variables in both the x and the y side. We're not going to need to list our variables in the x side because nothing is happening in the x side. So I'm just going to go ahead and list my variables in the y side, delta y, v initial in the y, v final in the y, the acceleration in the y, and time. And as we've talked about, we know that our acceleration in the y is always going to be negative 9.8 meters per second squared. We're trying to find our time, so that's my question mark. We want to put in our initial velocity, which we're given as 18 meters per second. And then we have to stop and consider what's happening with the rest. The ball bounces straight up, and we want to calculate the time it takes the ball to reach its maximum height. So I don't know delta y, but I do know the final velocity in the y when it reaches the top of its flight. Hopefully you remember when we went ahead and we looked at a projectile moving in an arc, we said when it gets to the top of the arc, the velocity in the y direction is 0. That's going to hold true when we throw a ball straight up into the air as well, so we know our final velocity will be 0. So I'm going to go ahead and get rid of all that. And now that we've got our variables listed, we can go ahead and we can try and find the time. I'm going to go ahead and I'm going to pick my acceleration equation and see v final in the y is equal to v initial in the y plus the acceleration times the time. And then I see that 0 is 18 meters per second minus 9.8 meters per second squared times time. And when I throw that into my calculator, do just a little bit of algebra, I should see that the time is equal to 1.84 seconds. I encourage you to pause the video here and make sure that you would get the same thing for the time. The next part of the problem asks us to calculate the maximum height the ball reaches. Well, nothing has changed, so I'm going to go ahead and use the information I already have. I'm going to use my position equation now, and I'm going to find that maximum height. So go ahead and write that out. So delta y is going to equal that 18 meters per second times that 1.84 seconds plus 1/2 times negative 9.8 meters per second squared times that 1.84 seconds. And we have to square that entire quantity. A lot of people have been forgetting that squared term over here. That's not optional. You do have to go ahead and square that term. So go ahead and pause this here and see what you get, and then come back and check it. All right, hopefully you got that delta y is 16.53 meters. And that is going to be a positive value because we know the ball is going up. It will eventually come back down, but we're not worrying about that part of the problem yet, okay? Until now. Now it says calculate time it takes the ball to get back down to the ground. well, I could calculate that, but remember we talked before again about this simple arc. We said that the time it takes to get to the top of the arc from the bottom, from where we throw it, is exactly the same as the time it takes to get from the top to the bottom, assuming that the ball is launched and lands at the same height. So we can use that and say, well, wait a minute, I don't really need to calculate. I have just determined that the time it takes to go up is exactly the same as the time it takes to go down. So my time to get down is 1.84 seconds. That means that the total time the ball spent in the air is 1.84 plus 1.84 seconds. And I can throw that in my calculator, but I should see that I get about 3.67 if I haven't taken any rounding into account. Now, we have a second problem here. A second rubber ball bounces straight up off a table with a velocity of 14 meters per second. I would like you to go ahead and start to finish, go ahead and try that problem now before I do it for you. Okay, hopefully the first thing you did was you went ahead and listed out some variables. Okay. And it would have been nice if I had asked you to actually do something here. I guess I should have done that. Let's go ahead and find the, let's go ahead and find the time the ball spins in the air. So I'm going to go ahead and list my variables. And you can pause if you weren't sure what to do with this one and maybe try it now, because we've got some interesting information here. Okay, so the time the ball spins in the air, that means I want to know the time it took to get up and all the way back down. So my delta y is 0. My initial velocity in the y, they told me, was 14 meters per second. And you might be tempted to put that your final velocity in the y is a question mark, but it's not. We remember from earlier on in the unit that if I launch and land at the same height, my initial velocity is exactly the same as the final velocity, only it's opposite in sign. Then my acceleration in the y is negative 9.8 meters per second squared, as it always is, and the time is the only thing I don't know. The easiest equation to use here is going to be our acceleration equation, because we know both velocities and the acceleration. So I get negative 14 meters per second is equal to 14 meters per second minus 9.8 meters per second squared times time. So if you do a little bit of algebra, you throw that in your calculator, you should see that the time is 2.86 seconds. So you should see that these problems are exceedingly similar to the ones we've been doing previous in the unit. The only thing is now we have an angle of 90 degrees, so we don't really need to use that trig anymore. We just need to realize that the velocity in the x direction will be 0, and the velocity in the y direction will be all of the velocity that we were given. Now we've got some example problems for you to work on in the rest of the packet, and we actually have a lab for you as well. Even if you're at home, you can go ahead and do this lab if you have a piece of tape and a ruler. So I would encourage you to go ahead and try this lab at home if you can. If not, you can come into class and make up the lab. But after that, you will see that there are several additional problems that you should be working on. All right, good luck with those, and see you soon.